The massive Somova-Parchesk Aquatic Complex spans 9,170 hectares across the lower Danube basin. It is a dynamic biodiversity hotspot, but its position at the edge of the delta also makes it a terminal sink for surrounding municipal and agricultural runoff. Many pharmaceuticals exhibit a property known as pseudopersistence. While these compounds may break down quickly under natural conditions, the daily emission from human infrastructure outpaces that degradation rate, resulting in a constant baseline concentration in the water column. The ecosystem is continually exposed to contaminants of emerging concern, or CECs. In the water column of the lower Danube, this includes highly active classes of drugs, broad-spectrum antibiotics, non-steroidal anti-inflammatory drugs, and anti-epileptics like carbamazepine. While these trace concentrations are typically below levels that cause immediate mortality, they result in chronic, long-term exposure. In aquatic biota, fluoroquinolone antibiotics are shown to fragment DNA and induce severe oxidative stress. Exposure to the antifungal clotrimazole drives the masculinization of female fish. Because these compounds interfere with normal physiology at such low levels, traditional water quality metrics like pH or dissolved oxygen are insufficient for assessing actual ecological hazards. Accurately modeling this hazard requires a dual matrix approach, quantifying the immediate environmental exposure in surface water while tracking the accumulation of chemicals in the tissue of native species like the common carp. Different organs serve as distinct toxicological records. The gills provide a measure of immediate water exposure. The liver acts as the site of metabolization. The fillet tissue allows for the evaluation of the compounding hazard for human consumption. The analytical hurdle is incredibly significant. The methodology must strictly extract, isolate, and quantify specific target compounds at nanogram per liter concentrations, pulling them out of complex, heterogeneous samples of water and biological tissue. This requires a strict analytical pipeline. The workflow strips away environmental noise through targeted extraction and chromatographic separation, terminating in exact molecular mass conformation. Executing this methodology across both water and biological matrices provides a complete dataset of the physiological stressors present within the ecosystem. The first node of the pipeline isolates targets from the water matrix. Using a Dionix Vradotrace 280 automated system, 100 milliliters of environmental water is pumped through a solid phase extraction, or SPE, cartridge packed with a C18 silica phase. Before extraction, the water sample is adjusted to a pH of 3 using glacial acetic acid. This suppresses the ionization of acidic pharmaceuticals, forcing them into a neutral state, so they bind to the hydrophobic C18 material as the water flows past. The cartridge is then flushed with ultra-pure water and a 20% methanol blend to strip away non-target polar interferences. The phase is dried completely under a stream of ultra-pure nitrogen gas for 5 minutes. To recover the analytes, pure methanol is pushed through the cartridge, breaking the hydrophobic bonds. The resulting liquid is collected and evaporated under a nitrogen flux at 42 degrees Celsius. The extracted analytes are redissolved in just 250 microliters of solvent. This step reduces 100 milliliters of river water down to a single concentrated droplet. This solid phase extraction solves the physical volume problem. It amplifies the trace chemical signal to a density that downstream mass spectrometry can accurately detect. Biological tissue presents a more difficult chemistry problem. Fish organs are dense with complex proteins and heavy lipids that can coat and interfere with the internal components of analytical instruments. To bypass this, the tissue goes through the Queacher's methodology. The biological sample is homogenized in water, acetonitrile, and formic acid. Then, a precise blend of dry salts is added: anhydrous magnesium sulfate, sodium chloride, and sodium citrates. This triggers a salting out effect. The influx of ions alters the polarity of the liquid. After spinning in a centrifuge at 4,000 RPM, the mixture separates. The target pharmaceuticals are driven upward into the acetonitrile layer, while the heavy proteins collect at the bottom. The acetonitrile supernatant holds the analytes, but it also carries dissolved lipids. It requires a secondary purification step known as dispersive solid phase extraction. Sorbent powders, primary secondary amine, C18, and graphitized carbon are added to the liquid. These materials bind and strip out the remaining lipids, sterols, and pigments. Queachers bridges the gap between biological tissue and analytical chemistry. It recovers the target pharmaceuticals while systematically removing the biological matrix around them. Exactly 10 microliters of the purified extract is injected into an ultra-high-performance liquid chromatographer, equipped with an AccuCore C18 analytical column. This graph tracks the mobile phase gradient over a 20-minute run. The system starts at 100% aqueous solvent and linearly ramps to 100% organic methanol. As the solvent shifts from polar to nonpolar, the pharmaceutical molecules release from the column one by one, separating according to their individual hydrophobic properties. Before analysis, the compounds must pass through a heated electrospray ionization interface to transition from a liquid stream into an ionized gas. At 350 degrees Celsius, the liquid eluent is vaporized. A 2800-volt charge is applied, forcing target molecules into the gas phase as intact charged ions. Chromatography and electrospray ionization transform a chemical extract into a temporal stream of isolated molecules ready for interrogation. The final node is the mass analyzer. The ions enter an Orbitrap Exploris 120, operating in both full-scan and tandem mass spectrometry modes, where they oscillate around a central spindle electrode. The data acquisition parameters are highly specific: an automatic game control target of 3 million ions, a maximum injection time of 200 milliseconds, and a scan range from 130 to 1,000 mass-to-charge ratio. The Orbitrap operates at 120,000 full width at half maximum. This produces a razor-thin peak that measures the molecular mass with enough precision to separate two nearly identical chemical formulas. This level of resolution is required to distinguish the mass of a pharmaceutical from isobaric background noise molecules native to the river water that weigh almost the same amount. High-resolution mass spectrometry removes ambiguity, providing definitive proof of a specific molecule's concentration inside the sample. Solid phase extraction, Queachers separation, liquid chromatography, and Orbitrap analysis comprise a specialized gauntlet. Each step suppresses environmental interference, isolating the target chemicals. These complex mass spectra represent physical molecules circulating through the Somova-Parkash lakes. Quantifying the nanograms per liter of pharmaceuticals in the gills, liver, and fillet of a fish provides a chemical record of the physiological stressors impacting the population. Combining advanced mass spectrometry with multi-matrix sampling establishes a measurable record of the pharmaceuticals currently altering the biological baseline of the delta.